Our next speaker is Michel Weber from ETH Zurich. All right, and as soon as he's all mic'd up and ready to go, then he's going to tell us about relaxing alias analysis.
Nice. No idea what that is. I'm. Yeah, full. Now full screen, please. Nice. Perfect. Oh, it's gone. And it's back. Okay, looks good. So, yeah, welcome everyone to my presentation. I am Michel Weber. This is work I did with Theodoros, Theodoridis, and Zhendong at the AST lab at ETH Zurich. And so I don't think I need to tell you here at PLDI that programming languages and programs are interesting and cool. And in this talk, I want to focus on how we make them run, which is through compilation, through a compiler. So a compiler is essentially a piece of software that translates a program in a sort of high-level source language to a low-level assembly file, binary size, binary file, something like that. And of course, there are many binary files that have the same semantics as the input source program. So modern compilers try to achieve actual good binaries. Well, and how they do that is that they optimize their programs. They try to remove that code. They try to vectorize stuff, whatever. Now, some of these optimizations that we want to apply are not sound in general, so we need some way of guaranteeing that they are sound. This is done through an analysis framework, usually. This analysis framework derives program facts like 2 pointers don't alias, and then the optimization can take these program facts and, I don't know, vectorize some matrix-matrix multiplication or something like that. So now there's this intuition or assumption in the community that, well, if we have more precise analysis, so analysis that gives us more information, then we will have better binaries, right? And that's really intuitive because more information means more optimizations, and more optimizations means a better world, right? And here in this piece of work, we're really trying to understand whether that's really the case. We're trying to shift this perspective and ask this question whether more precise alias or more precise analysis in general mean better binaries. So for this work, we focus on one specific analysis called the alias analysis. And the alias analysis is really about understanding the relationship between memory regions that different pointers point to. For example, at least how it's implemented in LLVM, you ask for 2 pointers, pointer 1 and pointer 2, how is the relationship between their memory? And then the alias analysis goes off, does fancy computation, comes back and gives you one of 4 results. This might be a may alias result, meaning I wasn't able to derive any guarantees. I don't know really. We have the no alias results, meaning the 2 memory regions are guaranteed to not be the same whenever or for this entire program. Then we have the partial alias result. This is about overlapping memory regions and sub-objects and stuff. This is really rare, but I still decided to include it for completeness. And then we have must alias, meaning the 2 memory regions are guaranteed to always be exactly the same. And now how this is implemented, at least in LLVM, the version that we instrumented for this work, is that we have the optimizations. They do fancy stuff up there, and then they ask the questions. Do the AI algorithms, the algorithms compute something, and then they give the information back. Good. So far, so good. So the question we're really asking here is, does more precise alias analysis mean better binaries? And now, to study this, of course, what we need is that we need to simulate several levels of alias analysis, essentially. And how do we do this? I think there are essentially 2 choices, really. You can go down through this lattice, and this is really hard, right? Because you run into all of these annoying issues that have to do with soundness. Like if you have a may alias and you replace it with a no alias, that might not actually be true, and then your program is not correct, but maybe non-deterministically not correct, and blah, blah, blah. It's an extreme headache. So we take the other choice, the, I think, smarter choice, which is go up. We just replace information that we have, no aliases, for example, with a may alias. So we're kind of taking away information from the compiler, and we see how does the performance of the binaries change. And this is really guaranteed to be sound, at least, I mean, conceptually, this is guaranteed to be sound, of course. There can be compiler bugs, but yeah, those never happen, of course. So how do we implement this? Essentially, we intercept the responses with this relaxation logic here, and then we can configure this relaxation logic for our different experiments to choose specific queries and bits of information that we take away from the compiler. And here, we decided to take away the second bit of information, changing a no alias to a may alias. Good. Going back to the high-level question, we know now how to do this technically. So let's ask more specific questions, and these are really our research questions. So our first question is, what is the impact of aliasing information? And this is really trying to compare the two extrema in this search space, the extrema of all the information and no information at all. Then the second one is, how much aliasing information is actually critical? So how much information does the compiler really need to still achieve the same result? Or if I were to formulate this the other way around, non-critical information is information that we can take away, we can give it, it doesn't really matter, we don't see an effect. And then our third question is, how impactful are these critical alias queries? And this is really about understanding the space in between the two extrema. What happens if we give a bit of information here and take away there, and yeah, see what happens. Okay, let's go through these. First one, what is the impact of aliasing information? The experimental setup here is very simple. Our relaxation logic just takes away everything. It relaxes everything to may aliases. This really corresponds to not doing any alias analysis whatsoever. And now we have this compiler version. So we use the SPEC CPU 2017 benchmarks, and we compare all information versus no information. And this is what we get. So how do we read this plot? On the x-axis, we have the different SPEC CPU benchmarks, 12 or so. On the y-axis, we have the relative time. So this compares the geometric mean of 10 runs for both versions. And if you're at 100%, that means they're equally as fast. If you're above the line, that means taking away information makes the program slower. If you're below the line, and there are actually points below the line, it means that taking away the information makes the program faster. So what we see here is we have one extreme case, this NAB benchmark that has like 5.5% slowdown or so. Most of the cases are in between like 0 to 2% or so. There's even speed ups. So at least I think this aliasing information has little impact actually. Everything is surprisingly little, given that we believe that so many optimizations are actually need aliasing information. So this is the question to our first, or the answer to our first question. Now for the second one, how much aliasing information is actually critical? The experiment that we designed here essentially runs one compilation for every query, and in that compilation it takes this query away. So for the first one, we take away the first query, second one, we relax the second one, and so on. For the 100th compilation, we relax the 100th. And then we get a lot of binaries, and then we really do a byte-wise difference to the initial binary where we had all of the information. So the critical ones are the ones where there is a difference to be found in this final binary. Good, so what are the results? So how do we read this from left to right? The first thing is the number of queries, the numbers of bits of information in general that the compiler needs to compile all of SPEC CPU 2017. There's around 5.5 million requests for aliasing information. Of these, 3.5 million are precise, so they are no, partial, or must, which are also the interesting ones for us because these are the ones that we can actually relax. Right, for a May alias, we can't do anything. And now of these 3.5 million, there is only a little bit more than 100,000 for which we saw a change in the final binary. So that's around 3%, which I think that's a crazy result. It means that 97% of the aliasing information that is requested by the AI algorithms doesn't end up having an effect on the final thing that is generated. So I think what we can say here is definitely that much aliasing information is actually not being used by the compiler, as we can see. Now, let's go on to the third question. How impactful are these critical alias queries? And to answer this question, the experiment we designed is that we essentially handed a coin to our relaxation logic, and on each query, it would just flip that coin. And then with 50-50 chance, it would relax the query or it would not relax the query. So here we ran 10,000 runs of this randomized alias analysis compiler version for every compilation unit. And then we had a lot of binaries. We measured their binary sizes. And in this next plot, I will show you the minimum, so the smallest binary that we achieved for every compilation unit. So how do you read this? On the x-axis, we have the around 1,600 compilation units for this benchmark. And then on the y-axis, we have again the relative time. So comparing the relative size. So we are comparing the size of the smallest randomized thing with the initial one. And we see that, of course, for many of them, there is actually fairly no real impact, it seems. But then there are some extrema that are kind of crazy. So we got a 40% reduction in binary size by taking away aliasing information, which I think was very surprising. And this is really not a trivial program. This is, or a trivial compilation unit. This is the variable length integer decoder of one of the compression benchmarks. So it's actually a core part of the functionality of that benchmark that we were able to reduce by so much. Now, I would love to press my button and show you the same results for speed. Unfortunately, we computed that doing this experiment for speed and running all the binaries would take something like 2,000 years. So we didn't end up doing that experiment. But we still, given that everything is randomized, we just gave it a shot, ran a couple of things. And what we found is that we couldn't evaluate everything. We found one case in particular where we found a 20% speed up by taking away aliasing information, which I think is another crazy result in this work. And then, of course, we went and investigated, both this the speed up result and also this size change. And it turned out for the size change, it appears that taking away aliasing information means that some dead store elimination is not triggered. If that dead store elimination triggers, so with aliasing information, we have more phi nodes, and then simplify ZFG can't understand the data flow and everything anymore in the program and doesn't apply as well anymore. And similarly, actually, in the speed up case, what we found is that it's again a dead store elimination that is not triggered, and then simplify ZFG that doesn't remove an entire basic block from the IR. And if that basic block is there, so if you take away the information, then this changes the code layout of pretty much everything, and that seems to lead to this 20% speed up. So it seems that the layout is just more cache-affine. Cool. So I think we can answer this with the critical queries. They can actually have high impact. Even though it's rare cases, they can have high impact. Good. So let me reiterate the results quickly. What is the impact of alias queries, of aliasing information? Well, it turns out it has surprisingly little impact, at least the two extrema. Then, how much aliasing information is critical? Well, much aliasing information is actually not utilized by the compiler, at least by this version of the compiler and in its current state. And then, how impactful are these critical alias queries? Well, it turns out that by having the aliasing information, the compiler is actually losing quite a bit of potential that we could have exploited. So let's get back to the high-level question. Does more precise alias analysis mean better binaries? Well, I think we can say now it's quite a bit more complicated than that, in fact. And I really want to stress here that this is not an issue with alias analysis or aliasing information or something like that. I think it's more about how the compiler uses that information. And I, at least to the best of my knowledge, I think this is the first work that actually analyzed this, at least in this fine granularity of actually looking at specific queries and not just comparing different AA algorithms. But what do our results mean for the compilers community? I think that rather than focusing only on improving alias analysis, which in itself is definitely important, and we should do that, right? We should have better AA algorithms and everything. I think we should try to identify and then improve on the critical information, so the information that really matters, and then that the compiler should also get a bit better at actually utilizing the aliasing information, not just 3%, and also not missing these extreme speed-ups in the corner cases. So thank you very much. I'll now take questions.
Oh, go ahead.
Hi, great work. Just a quick question. Have you also considered categorizing the impact of these information based on which passes are consuming it? Like instead of dropping the information altogether, dropping it for a particular pass?
Yes, we have. Let me just quickly find that. So what we see here is first we have the different passes that actually request aliasing information. Then we have number of precise ones, number of critical ones, and then the percentage. And we really see that it matters a lot. The pass is really, really important.
Okay, all right, thanks.
Hi, George Washington University. So could you elaborate on what alias analysis algorithm you tried? Because alias analysis algorithm can be really expensive, so that is critical to provide different sorts of informations.
So this is really built on LLVM 17.0.6.
So LLVM's own alias analysis, the
Yes.
basic one.
So there is multiple alias analysis algorithms in that version. I think that's basic alias analysis. There's some metadata, type-based stuff. There's several versions. We really try to not look at the AI algorithms themselves. Though I think this is a limitation of this work, that I think sometimes criticality can really depend on the other information that you have available. So if we had the perfect aliasing information,
Sure.
maybe 3% is not correct.
Yeah, thank you.
Nathan Beckman, Carnegie Mellon. I'm trying to reconcile this great talk with my experience where alias analysis has a huge impact. I'm wondering, have you looked at other architectures than an out-of-order superscalar? Because I think having a giant LSQ with all the structures to support speculative execution are maybe part of what's hiding the potential impact here in the compiler.
So we really only evaluated this on one specific version CPU, which was I think it's an AMD EPIC CPU, I think. I could have to check the paper. We really didn't look any further.
That might be another area to take this
Yeah.
kind of work. Thank you.
Thank you for the suggestion.
Hi, I'm Zhendong Lee from KLAIS. So I guess your message is that we should try to utilize alias information better, and in other words, I guess you're saying that. Then my question is, did you find I guess you looked into certain LLVM optimizations, and did you find any cases where you thought that for this optimization, alias analysis could be utilized better?
So I can't tell you for specific optimizations, but I can tell you that what we found is that sometimes really sets of information together lead to optimizations. And this is something that the current AA framework in LLVM doesn't really understand. So I think that's where we could actually improve, by understanding these sets of information, essentially.
Thank you.
I think we're going to have to cut off questions here. I know there's a lot of excitement, but Michel will be around to talk.